Hi again, it's Liam. Welcome to lecture number 3 on electricity, and this one is about drift velocity and conductors, insulators, all that kind of jazz. Right, so we're going to start it as usual by looking at what we've got to achieve today, and that is be able to demonstrate, define and apply mean drift velocity of charge carriers. We're going to define what it means and how we use it. The equation I equals ANEV, we're going to look at what these terms are and how we apply it. And conductors, insulators and semiconductors, what they are, what differs them, and why they behave the way they behave. So, first thing we're going to look at is graphene. Now, graphene is a very, very famous material which is like changing the world. It's some incredible material. And the way that it's doing that is because of a very interesting property about its structure. Its structure allows for lots and lots of strength, lots and lots of thermal conductivity behaviour, but it also does something which is incredible, which it allows for a lot of free electrons. And that number of free electrons means that it can behave very, very, very highly conductively, and that it's very easy to pass a current through it. Right? That number of electrons, that number of free electrons, is what distinguishes the 3 different types of materials: conductors, insulators and semiconductors. We have something called the number density, which is how many free electrons there are per unit volume. And that, as number density goes up, so too does conductivity. So, right at the bottom, with the lowest number of free electrons per unit volume, we have our insulators. That is things like rubber and wax. These things have a very interesting structure in which their large ions are holding onto their electrons incredibly tight. They ain't going to let go of them anytime soon. So we have to try very, very hard to get the electrons to move and to get a current to flow, which is why they have a very low number of free electrons. People like this guy who don't have a local creep holding onto them, also known as an ion, right? We move up our number density chain and we get into our world of semiconductors. There are more free electrons per given volume in semiconductors. Now, they behave differently as well, and we'll talk about the proper use of these and how they behave, but for now, we just need to know they have a sort of middle range number density, or number of free electrons per unit volume. Right at the top of this we have conductors, things like lead and copper, and they have so many free electrons because the very nature of their metallic bond allows for free electrons even when they've got a local creep. He's a local creep who doesn't mind sharing as long as he's got spare electrons in the periphery. So they have like a cloud of available people to creep on, but they will allow transitions between those electrons, if that analogy isn't too weird. Now, you might imagine that when you walk up to a light switch, for example, in this room or anywhere in your house, and you just flick a switch, the light switch turns on immediately. And as a result, you wouldn't be a fool for thinking that electrons would rush into the bulb and that's what's causing it to emit light. But in fact, they don't rush very fast at all. Something rushes fast. The energy must be rushing fast. There must be some information communicated between here and there. But it isn't electrons. The electrons themselves take quite slow, languid paths. And that's why we call it the drift velocity. And that drift velocity is to do with the fact that the electrons make lots of collisions with all these massive positive ions which take up most of the space that they're in. So the drift velocity itself is actually quite a small number because they only need to sort of net move in this direction. As long as charge is moving around, the net charge is changing in the area, they don't need to be moving particularly fast as long as there's a lot of them generally moving in that direction. Drift velocity actually much slower than the individual speed of a single electron making its journey. They could be going really fast in one direction, they could even be going backwards. The net movement of this wiggling and bashing into other things is in the way that the electron flow is going. Conventional current going in the opposite direction, obviously. You need to remember that. Now, what we're going to do is we're going to look again at our aims for a second. We have discussed what it means by the mean drift velocity, and we've looked at the difference between conductors, insulators and semiconductors. Now we need to think about this equation, I equals ANEV. What you're going to have to do is pay a lot of attention here and maybe pause the video and take notes, because I'm going to be going through how we derive the equation I equals ANEV, where I starts out being the current. This is an equation to represent current. So we start out with the original equation, current equals charge over time, or the rate of change of charge. And we start by thinking, how can we express these terms in a different way? So we're going to think about the total charge on a thing as being equal to the number of electrons times the charge on an electron, if we think that the electrons are representing the only charge available to us, right? So the number of electrons times the charge on them, that's the total charge. How do we work out the number of electrons though? Well, we have to go back to this idea of number density, our number of electrons in a free space, in a given volume. So we work out the number of electrons by timesing our number density, which should be a constant for each material. We times our number density by the volume of material that we've got in front of us. And that will tell us how many electrons we have within that material, or more importantly, how many free electrons we have within that material. If we do that and combine those two ideas, we can see that the total charge is equal to the number of electrons, which is n times v, the number density times volume, the number of electrons, which is these two, n times v, times the charge on an electron, our fundamental charge, our elementary charge, whatever we called it the other day. So Q equals n, the number density, times the volume, times the charge on an electron, right? That is our total charge. Now all we have to do is put this equation in instead of Q. So wherever we have Q, we're going to write NVE instead. So we get I equals NVE over delta T, or current equals number of charge carriers, or number of free electrons, on number density. I equals the number density times the volume times the elementary charge divided by the time. Now, we can see again, if we look below, how can we express some of these terms in a different way? Well, volume is equal to the area times the length. So we're going to shove that in instead. We're going to have, instead of volume, we're going to have I equals number density times the area times the length, in place of the volume from before, times E divided by delta T. Well, we can also see this. We can see that L over delta T is the definition for velocity. Length over time, distance over time. That's speed, isn't it? Or velocity. Velocity equals speed over time. So instead of writing L over delta T, we're going to replace that with V. And that V is our drift velocity, and it finishes our equation. So that current is equal to the number of charge carriers, or the number density. Current equals number density times cross-sectional area times the drift velocity times the electric charge, or the elementary charge. That is an equation that you need to be able to remember, and being able to derive it couldn't hurt either. Do you understand? Let's hope so. Let's quickly check our aims then. Have we gone over what it means, what mean drift velocity means? I should hope so. Do we understand what this equation means? Can we apply it? You'll be able to test that in the questions below on the haiku. And we discussed this earlier on, the difference between conductors, insulators and semiconductors. You should be able to explain them in terms of their number density, or their number of free charge carriers in a given volume. Thanks for watching. See you.